Hello, this is Dr. Morton again. This is your video for Chapter 2, which really try and keep this one to about 10 to 15 minutes max. What I'm going to cover today is really the contents of Chapter 2, which is basically number systems and binary math, and we'll talk some about hexadecimal and conversion, and we'll talk a little bit about how we do math in the binary world. So let's get started. Okay, what we're going to cover today, first we're going to talk about number systems, and that involves the base, the point. We normally refer to it as the decimal point, although in URLs it's gotten changed a little bit, so people are used to calling it point. But when you put the point or the decimal point into a binary number, it's no longer the decimal point, because that refers to the decimal system. So it's really the binary point. So we're just going to use the word point. When you use it in a hexadecimal number, it's a hexadecimal point, or the hex point. So we're not going to call it that. We're just going to call it the point. And then each position of a number has an associated exponent, and we'll talk about that. And then we have to have a set of symbols to represent the numbers. Now, for the decimal system, that's easy. The set of symbols we use are the numerals 1, 2, 3, 4, 5, 6, 7, 8, and 0. 10 symbols, and that's all it takes for our base 10 decimal number system. For binary, we just need 2 symbols. So we use 0 and 1 and ignore the rest. But what about for the hex system? Well, we'll talk about that in a minute. But we need 16 symbols, and we only have 10 for the decimal system. So we'll talk about that. It's actually interesting, and my personal view is I think some mistakes were made. We'll also come back and talk about how we do conversions from one number system to another. First, note that whenever we do these conversions, we always do all the math in decimal. Secondly, we have to convert the integer portion of a number to a different base separately than we do the fractional portion. We have 2 different methods to do this when we're doing it by hand. Then we're going to talk a little bit about binary math operations. We'll talk about addition and subtraction. I'll talk about multiplication. I'm probably going to skip over division. It's a little more tedious. I'll talk about it very briefly. I'm not going to really work through too many problems because, division is an important operation, but it turns out that all of these operations work out to be addition, all of them. Subtraction is addition, multiplication is addition, division is addition. And I'll show you how that works. At least in the digital world, that's true. And that's because we use a special format for signed numbers that allows us to just add them to subtract them. So, all right, or at least to use the same adder as a subtractor, and we'll talk about that. And finally, then I'm going to talk about some key points for logic design when it comes to this number system world. The conversion from binary to hex, which turns out is very simple. Why we use a hex? The difference between a binary representation inside a computer, a binary coded decimal representation, which is pretty antiquated but still is used some, and finally the ASCII representation inside a computer. Sometimes we refer to these as codes, and we will talk about codes down the road. So we're going to cover all this. But first, we're going to talk about number systems in general. Okay, here we are in Chapter 2 of the Logic Design book. And so this is our number system. The learning objectives include, we want you to be able to convert from decimal to binary. We want you to be able to convert from binary to decimal, the other direction, that obviously. We want you to be able to convert from binary to hex and vice versa. And we want you to demonstrate the ability to do signed binary addition and subtraction using 2's complement numbers. We'll explain what 2's complement is. And then we want you to understand how unsigned binary multiplication and division can be done. I'm not going to talk about signed binary division and multiplication because those get rather weird and complicated. And you shouldn't really have to deal with that in your career because those problems have already been solved, and you should just use the existing solutions It's more tedious than it is intellectually deep, but it is tedious. Here's some of the key glossary things. Binary numbers use the base 2. Hexadecimal use the base 16. And the base is the integer that defines the meaning of all the symbols and their exponents in the number system you're using. 2's complement, we'll talk about that, and 1's complement and sign of magnitude, which are kind of the competing ways to represent negative numbers. But almost all systems use 2's complement. Not quite all, almost all. All right. So all number systems are based on a base, and then we use symbols to represent them. So for instance, in the decimal system, when we write a number like 327.52, the position of the 3, the 2, and the 7, the point, or the decimal point in this case, since it's a decimal number, and the 5 and the 2, the position of those symbols, and again the symbols are 0 through 9, the position of those symbols related to the point is critical, because that determines each of those symbols and the value that they represent are multiplied by the base raised to various powers. So for instance, for the 3, we take the base and we raise it to the power of 2, which means 10 raised to 2 or 100. So that's 3 times 100, or that 3 represents 300. The 2 represents the base raised to the 1 power, so that's 10. So that's 2 times 10, or 20. Oh, you know what? I think, hang on a second. Okay, I took a little break there to make sure that I had turned on the cursor, but I know you can't see the cursor, so that's a little bit disappointing. But I think maybe if I highlight it, you can see that. Yeah, okay. So that's the number I'm talking about, 327.52. So notice we use these symbols 3, 2, and 7, 5, and 2. So the position relative to the decimal point determines what the value of those symbols actually is. So the 3 is 300, the 2 is 20, 2 tens, the 7 is 10 to the 0 power, which is 1, so that's 7 times 1, or 7. And then on the right of the decimal point, we use decreasing powers. So starting from the decimal point, working to the left, we use increasing powers starting with 0, because 0 is a positive number. So we use positive powers on the left, negative powers on the right, and we start with 0 when we start going to the left. On the right, though, we start, our first position is a -1. There's no -0. There's a -1, and so that's 5 times 10 to the -1, or 5 times 1/10, or 5 tenths. And then 5 times, then 2 times 10 to the -2, are 2 100ths. So that's 52 100ths, or 0.52. Now, just a little point here. Whenever you want to maintain high precision, you avoid using decimal places. And you represent fractional portions as integer ratios, where you completely preserve. The problem is, what if you want to represent 327 and a third? Well, you can't accurately represent that with a decimal number, because you need an infinite number of decimal places to get it exactly right. And that's ridiculous. You can't deal with infinite. So if you really want to maintain the fractional portion perfectly, you have to represent it as an integer. So you would have to write 327 plus 1 divided by 3, or 1/3. But and a number of programs actually do that to maintain a very high degree of precision, because if you don't do that, then you get into trouble. But it does complicate the math a little bit, and it makes looking at stuff more confusing. All right. Okay, so that's how this works. And let me scroll down. You can see it right here. Here's 327 laid out. 3 times 10 squared plus 2 times 10 to the first plus 7 times 10 to the 0 plus 5 times 10 to the -1 plus 2 times 10 to the -2, or 300 plus 20 plus 7 plus plus 5 times 1/10 plus 2 times 1/100. All right, so that's really, when we write 327.52 in decimal, that's what we mean. And often we'll represent it with a little, like this, with a little lowercase 10 over here to represent that we're in base decimal, base 10. Now, we don't only use this briefly. We're not gonna write this very often, but every now and then we will. So here's 43.75 base 10. Here's 2b.c base 16, so if we translate the 27.5, or sorry, if we translate 43.75, that works out to be 2b.c in base 16. Okay, we're going to go over how to do that in just a minute. Okay. So for the decimal system, our base is 10. We have the 10 symbols, 0 through 9, and we use the point, or the decimal point, as our reference for positive values of the exponent. So 10 raised to 0, 10 raised to 1, 10 raised to 2. And on the other side of the decimal point, the right side, we use minus exponents. 10 raised to the minus 1, minus 2, minus 3. Remember, we start with 0 on the left side, but we start with 1 on the right side because there is no minus 0. 0 is a positive number. Okay. Now, so it's easy to convert from any base to decimal because we just write it out in that form we just looked at with the base raised to the various powers depending on the position of the symbol on either side of the point, and that works out. Okay, what about binary? Well, you know, in binary, our base is 2, and we are going to use powers of 2 starting at the decimal point, positive powers working to the left, negative powers working to the right. So this number is going to be, so here's our decimal point. We'll put it over here. So this is going to be 0 times 2 to the 0 plus 1 times 2 to the 1 plus 1 times 2 to the 2 plus 0 times 2 to the 3 plus 1 times 2 to the 4. Well, 2 to the 4 is 8. 1 times 8 is 8. 0 is times 2 to the 3. 2 to the 4 is 16. 2 cubed is 8. 2 squared is 4. 2 to the 1 is 2. And 2 to the 0 is 1. But 0 times 1 is 0. 1 times 2 is 2. 1 times 4 is 4. 0 times 8 is 0. And 1 times 16 is 16. So we get rid of these because they were zeros up here. Sorry, I got things out of kilter there. All right. And then we have to deal with the fractional portion, which we left up here, right there. So now we deal with this. Well, that is going to be 1 times 2 to the minus 1 plus 1 times 2 to the minus 2. Well, 2 to the minus 1 is 1/2, and 2 to the minus 2 is 1/4. So 1/2 and 1/4 is going to be 3/4 or 0.75. So to convert this to decimal, so we're going to put 0.75 over here for the fractional portion. And now for the integer portion, it's 16 plus 4, that's 20 plus 2. So the final answer is going to be 22.75. And that's what this number up here equals, 22.75. And the way you do it is you just take each of these symbols, multiply it by 2 to raise to the power, starting with 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 4, 2 to the 0, 1, 2, 3, 4. So it works out to be 1, 2, 4, 8, 16. And going this way, it's 1/2, 1/4, 1/8, and so forth. All right, so that's how we convert from any base. In this case, it's base 2. if we did the hex number that we looked at earlier, which was 2b point C, so we had a hex number of 2b point C. Now, what about this B and C? Well, okay. So I told you I was gonna deal with this when I went through the outline. When they came up with hexadecimal, they made a mistake in my view. They needed 16 symbols, but they only had 0 through 9. So they looked around, and instead of creating some brand new symbols for 10, 11, 12, 13, 14, 15, and 16, or 14 and 15, they just stole letters from the alphabet. So they stole A, B, C, D, E, F. Now, if you think about it, what could go wrong? Well, one thing that can go wrong is there are two representations for A and B. There's A and there's A. I'm sorry, for A, and for B, there's B and B, and same for C, D, E, and F. There's uppercase and lowercase. So when you type these in, and we use a code when we type things in simple situations we use ASCII, in more complicated situations we use Unicode or some of the other things. And we're going to cover all that. But what this means is now, when you type these hex letters in, you have to make special exceptions in the software to recognize lowercase and uppercase symbols for A, B, C, D, E, and F. And not only that, but if you write something like BAD, is that the word bad? Or is that a hex number? You don't know. Unless maybe somebody would write base 16 out here, or there's digits in it or something. But if you just had BAD, that's a perfectly legal hex number. It's also a perfectly legal English word. So I think they should have made some new symbols, but they didn't want to do that, and now we're stuck with this because this is universally used. Okay. So, let's look at how we would convert the hex number we talked about earlier, which in this case was 2b point C. All right, so that's going to be, we're started at the decimal point, so that's going to be b times 16 to the 0 power plus 2 times 16 to the 1. So that's 2 times 16, or 32, plus 16 to the 0 is 1. So that's b, which is 11. And then the decimal point, we have plus c times 16 to the minus 1, our 16ths. C is 12, so that's 12 sixteenths, or 3/4, or 0.75. So this would then work out to be 32 plus 11 plus 0.75 in decimal, or 43.75 decimal. So that's base 16, and it turns out to be 43.75 in decimal. And we do it exactly the same way for every base. In this case, the base is 16, and that's why we call it hexadecimal. All right. Okay, now I said at the beginning we'd talk about number systems and cover the base, the point, exponents, and symbols, and we've done that. So next, we're going to talk about the conversions. Well, we've talked about how to convert any base to decimal. That's pretty easy. The question is, how do you convert decimal to any base? That's a little trickier. And so that's where we definitely have to divide it into the integer and fractional portions. So first I'm going to show you how we go from decimal to binary. And then we'll talk, I may not do the decimal to hex. Of course you can use your calculator to do this. It makes it a lot simpler. But I would like you to do some of these by hand. And it just is good practice, so you demonstrate to yourself that you actually know how to do it. And then when you use your calculator, you know if the calculator is really lying to you. You got some sort of sense about the operations being done. And hopefully you punched the right buttons and the calculator did everything correctly. All right, so let's do this. Okay, so let's look at how we would go. Let's write a number. Let's do a simple number. Let's do say 47.2, and we want to convert that into binary, base 2. All right, how do we do that? 47.2 to binary. The first thing is we're going to deal with the integer portion, and then later we're going to deal with the fractional portion. So for the integer, we take 47, and we do this little funny upside down divide thing. So we divide 2 into 47, and 2 into 47 goes 23 times, with a remainder of 1. Then we divide 2 into 23, and that goes 11 times, with a remainder of 1. Then we divide 2 into 11, that goes 5 times, with a remainder of 1. 2 into 5 goes 2 times, with a remainder of 1. 2 into 2 goes 1 time, with a remainder of 0. And 2 into 1 goes 0 times, with a remainder of 1. So this is our binary number. Now what you have to do is be real careful here. This is the low order bit, and this is the high order bit. So we want to take it over like this and write it 1, 1, 1, 1, 0, 1. Just like that. Okay? So I think I can get this all on here. Yeah. Okay. So that is it. Now let's check it. So, well, we haven't done the fractional portion. We haven't done our 0.2 yet. We'll come back and get that in a second. Okay, so let's see. So we know these positions are 1, 2, 4, 8, 16, 32. So we have 32 plus 8, that's 40. Plus 4 and 2 is 6 and 1 is 7. 7, that's 47. Okay, so that checks with our integer portion up here, 47. So that's correct. So 47.2 equals 10111 point. Now we have to get the 2 right. 2 should be easy. So I should, maybe I'll make this 27 here. Something like that instead. All right. So 27. So what I want to do this part, I'm gonna write it down here. I'm gonna write 0.27, and I'm going to multiply it by the base 2. So 2 times 7 is 14. Carry a 1. 2 times 2 is 4, and 1 is 5. 2 times 0 is 0. All right. So the first bit to the right of the binary point, in this case, the point is going to be a 0. Then we're going to multiply this by 2. We get rid of this 0. 2 times 4 is 8. 2 times 5 is 10. The next bit is going to be a 1. Okay, so up here I'm going to write a 0. That was our first one. And then I get a 1. All right. Now I write 2 times 8. That's going to be 0.16. We get rid of this 1. And then, so that's another 0 here. And then I'm going to write 2 times 0.16. So that's going to be 0.32. So this is another 0. 2.32 is going to be 0.64. So that's going to be another 0. And 2.64 is finally going to be 1.28. And so that'll be a 1. And then let's see. Yeah. So I have not. I haven't. So then my 2.8, I double that, and that's going to be 56, 0.56. That's going to be a 0, and 2 times 56 is going to be 2 times 6 is 12. Put on your 2, carry your 1, 1, 1.12, and oh my God. So this one's not going to terminate for a long time. So I'm going to put a 1 down here, but I have not yet seen a repeating pattern. Eventually I will, but I have not seen a repeating pattern. Wait, where is it? Here. So look at all of the digits it's going to take me to represent the 0.27 here, and this is not accurate. I've got a little bit left over, so I need more digits, and I may eventually. It may never terminate. It's probably going to just keep going and eventually I'll get a repeating pattern of 4 or 5 digits. So we'll see. I didn't finish this out. That's one of the reasons why when we do these fractional portions in this, we call it, well, in base 10 we call them decimals. When we do these decimals, we get into trouble. And that's why if you really want accuracy, you have to represent the fractional portions as integer ratios. But that's okay. In this case, we would represent it as 27 100ths. And that's exactly precise. Now we can convert 27 as an integer into binary exactly, and 100 as an integer into binary exactly, and we can represent this 0.27 in decimal as a ratio of binary 27 to binary 100, and then we've perfectly captured it. But if we actually insist on working it out into these binary fractional portions, we're going to have a lot more digits before we finally get a repeating sequence. And even then, at some point, we're going to just have to stop, and it won't be. There'll still be a little piece left over that's going to be an error. All right. So hopefully you got that idea. And I'm taking more time. I'm already at 26 minutes, so I'm not happy about that. All right. Okay. Let's move on. Okay. What I'm going to do now is binary addition, binary subtraction. And yeah. All right. Let's do that. So let's say we have binary number 10110. I'm going to leave out the decimal point, the fractional portion this time, but it works the same way. Well, okay, we'll put in a couple. And 01011.01. All right, we're going to add these up. 1 plus 1 is in binary 2, and binary in 2 is written 10. So what I'm going to do, I'm going to write the 0 and carry the 1. 1 plus 1 is together 2. Put down your 0, carry your 1. 1 plus 1 is 2, carry your 1. 1 plus 1 plus 1 is 3. Well, 3 is written 1. So now I'm going to put down the 1 and carry a 1. 1 plus 1 is 2 again. 0, carry the 1. 0, carry the 1. 0, carry the 1. So when I add this number and this number, I get this number. And we can see what this number is because it's pretty easy. So this would be 1, but there's nothing there. 2, 4, 8, 16, 32. So it's actually, this equals 34. And this number is, so this number is 2, 4, and 16 are, that's 22 point, so it's 3/4 are 0.75, and this number is 1311.25, and 11.25 and 22 point is 34 exactly, 0.00. All right, so that checked. All right, so that's how you do addition. And it's pretty easy to do. How about subtraction? Subtraction's a little trickier, and I'm going to show you a trick that will make it easy. Let's take those same two numbers and subtract them. So I'm going to subtract 11.25 from 22.75. All right, and I'm going to do it two different ways. So first I'll write these numbers again. 10110.11 minus 01011.01. All right, so now what we do is we just add these up. We subtract. So 1 from 1 is 0. 0 from 1 is 1. 1 from 0, that's a problem. We can't do that. So now we take this 1, that leaves a 0 there, and we put a 2 here. And I just write the 2 in decimal, okay? And 1 from 2 is 1. Remember I said we really do all our math in decimal anyway, so you might as well just write the 2. All right? Now we want to do 1 from 0. We can't, so we have to cross out that, put a 0 there, and put a 2 up here, and we're going to borrow 1 from there, and that's going to be a 1. 0 from 0 is 0. 1 from 0, borrow this, put a 2 there, a 0 there. 1 from 2 is 1, and a 0 here. So this works out to be, if we do this, so this should be 1, 3, 11. So this should be 11.50. So 11.50. And if you take 11.25 from 22.75, indeed, it should be 11.50. Okay? So that's it. Now, I'm going to, later on, I think I'm going to, so we've got a few things left to do. I have covered addition and subtraction. I'm going to save multiplication and division and some of these other key points for another video. So I may do 2 videos for this one. I want to keep them short. And so this is already at 31 minutes, so I'm going to quit.